All right, aloha and welcome to Monday. See, we're getting smaller and smaller as we go. Guess we should pretend like we're gonna have a quiz the rest of the week so everybody shows up. I don't know when there's gonna be a quiz. Today we will finish off chapter 15 and jump into chapter 16, which will be what lab will be on this week, which is buffers. So let's finish off the last thing we were talking about on Friday. What was the last thing we were talking about on Friday, Valerie? Oh, Avery, you were here. What was the last thing we were talking about? I mean, but what was the specific things we were looking at? Anyone remember? Bryce, what was the things we were looking at? Very good. We were looking at the different pHs and stuff of cations or anions, and we were decide. So when we have solutions of cations and anions and their electrolytes, we call those salts. So when we talk about salts in chemistry, we're simply just saying dissolved ions. Yeah. So that's what we'll get into. But pH neutral just means it's an ion that does not add any protons or hydroxides. So anything that's pH neutral would be a anion or cation that doesn't affect the pH. What type of compounds do not affect the pH, Jack? Mostly correct. Leave out the weak. Okay. Anything that comes from a strong acid. So a strong acid is H and something, right? The H is obviously going to make a solution acidic because it's adding H plus directly. But the counter ion of a strong acid, which would be Cl minus, NO3 minus, Br minus, I minus, when we have the list of strong acids, all of those counter ions are what we call pH neutral, okay? Because they will not grab any protons off of water, which would thus make it a slightly basic solution. If we look at a actual ion that's actually going to be basic, we could think of something like F minus. Oops, hold on one second. If we're looking at F minus comes from HF, right? So HF, what type of acid is this, Alondra? It's a weak acid. And the definition of a weak acid means that it is going to be intact in solution some, right? And it's pretty significant the amount of intactfulness, right? If you calculate the percent ionization, it's probably way less than 10% ionized. So for the most part, that F minus, so when this dissociates into H plus and F minus, this F minus likes to grab H plus. So if we just had a solution of sodium fluoride, for example, we would expect that the F, so if it's NaF making Na plus and F minus, the F minus would react with water and it would grab the H off of water to make some HF, which would liberate OH minus. So the conjugate base of a weak acid will always give us a slightly acidic or basic. Which one would you expect it to be? Ian? So if it's making this OH minus in solution, would the F minus be acidic or basic? Guess one more time. Basic. Very good, right? Because you're generating OH minus. OH minus means basic. Things that make H plus would be acidic. So that's when that's just the F minus, okay? If you put HF in solution, it's definitely going to be an acidic solution because only some of the F minus is going to make OH minus, but all of the H plus is going to make H plus, so the solution would be acidic. So if you're finding the pH of a HF solution, you would expect the pH to be acidic. But now what we're looking at is what happens when we have ions in solution. So the take-home message is what Jack said. The conjugate base of strong acids. So what's the strong acids? HCl, HBr, HI, HNO3, HClO4. H2SO4 is a little bit weird because it's diprotic, so let's not consider that conjugate base to be basic. But the rest of them, Cl minus, Br minus, I minus, NO3 minus, and ClO4 minus, all of these are what we call pH neutral, which means that when those are in solution, they're just going to sit in solution and do absolutely nothing. If you think back to Ch15a, when you did all those solutions of like, we wanted to see what precipitated and stuff, remember we would switch out the cation, but we would always leave the anion as the nitrate anion. So it was like we would add like sodium nitrate, we would add things like iron nitrate, we would add all these things that had the nitrate, and the nitrate was pH neutral. It didn't react with anything. That way we knew that it's reacting with the cation, okay? So by that same concept, any of the strong bases, sodium, potassium, what else? Lithium, and then calcium 2 plus, barium 2 plus, and magnesium 2 plus. These are the conjugates of the strong bases. All of these things also will not grab OH minus out of solution. So and these are a little bit weird, but basically all of these ions here are pH neutral also, okay? Now, anything that's not the pH neutral ones, that means they're either going to be acidic or basic. The acidic or basic ones, you can usually look at the charts to figure that out. So for this kind of thing that I'm going to ask you on the test is, let's look at every single one of these examples, right? So we have strontium chloride, SrCl2. Do we have a periodic table? Let's pull one up. Periodic table. So strontium, I guess strontium is probably a considered a pH neutral also, but let's just verify that. Let's go back to our notes. So we're over here. So since strontium, so basically any cation in group 1 or 2 is going to be pH neutral. What does that mean? It's not going to affect the pH. So the strontium is pH neutral. Why is it saying that the chloride is pH neutral? Cade, why is chloride pH neutral? Yes, thank you for giving the definition of it. But how do we know that it's not one of the acidic or basic ones? What does the Cl minus come from? Which acid? No, HCl. So SrCl is a random salt that we're putting in solution. HCl is a strong acid. Remember, any conjugate base of a strong acid is going to be pH neutral. So if we see that the Sr is pH neutral, if we see that Cl minus is pH neutral, what does that mean that salt's going to do to the solution? It's going to be pH neutral. Everybody comfortable with that? Okay, let's look at AlBr3. Okay, that has Al3 plus and Br minuses. Let's do the Br minus first. What would we say Br minus is, Merve? Is it acidic, basic, or neutral? Everybody agree with that? Yes? Why, Bailey? And what is that list? So you can memorize a list or you can memorize what makes up the list. Jackson, what makes Br minus pH neutral? And why doesn't it produce OH negative? I'm looking to explain this in terms of strong or weak acids. Nate, what does Br minus come from? Which acid? Yeah, Bryce. HBr is a strong acid. Therefore, The Br minus is a pH neutral. So that means that this is not going to change the pH of the solution. Let's check if Al3 plus changes the pH of the solution. What would Al3 plus be considered? Is it one of the group 1 or group 2 metals? Yes or no? Let's look at the periodic table. Is Al, which is located right here, is it in group 1 or 2? No. So those of us who didn't get it, whenever you have a cation from a metal that's not in group 1 or group 2, it will be a slightly acidic compound. Okay? So this will be a slightly acidic. So then this solution would be an acidic solution. You see here, pH neutral, acidic. If you have a neutral and an acidic, what's it going to do? Make the solution acidic. Let's look at this next one. CH3, NH3 plus, and NO3 minus. Okay? That's me breaking it apart. I break apart the cation and the anion. I put the plus with the cation, the minus with the anion. Emily, is either of these pH neutral? Huh? What do you think, Ida? Is either of these pH neutral? Look at Bryce. Bryce is on top of it. Yes. Yes. Which one is Bryce? Very good. Why, Bryce? HNO3 is a strong acid. Do you think you should know the strong acids for this next exam? Only if you want to be successful, okay? So you don't have to come to class and learn, but if you want to be successful in a class, you should pay attention to it and talk about and listen to the things that we're talking about, okay? What about this CH3, NH3 plus? Is that pH neutral or not? Loit? Is it in the group 1 or 2 metals? Is that look like a metal with it has 7 different elements in it? No, it is not. So it's definitely not a pH neutral. It's either going to be acidic or basic. What's our thoughts on this? Any thoughts? Huh? It's going to be the conjugate base of a weak base. Okay. Anything with a nitrogen is a weak base. Okay. Especially with a positive charge. So therefore, it's going to be positive. What's going to happen when this thing reacts with water? What is that positive thing going to pull out of water? Take a guess, Kayla. Yes, it's going to pull an OH minus out of water. So it's going to make CH3, NH3, OH, which pulls an OH minus out of this. What is that going to leave? An H plus. So that would be an acidic cation. And we would say it is an acidic solution over here. Okay? So you have to break it apart into parts and figure it out. Yes. Nope. I don't want to spend that much time on this. Go ahead. Do it. I already came back. Talk about it. Ask it. It is a weak base with a plus on it, so it's the conjugate acid of a weak base. It is not a base. It is a base that added a proton. Just like when we're looking at NO3 minus, that's not an acid. That's the conjugate base of a strong acid. When it's HNO3, it's an acid. When it loses the H, it becomes a base. CH3NH2 is a weak base. And when it adds a proton, it becomes the conjugate acid. So the fact that it's a conjugate acid should also lead us to believe that it's probably going to be an acidic solution. Okay, let's look at this next one, NaCHO2. Any thoughts on this? Meredith, what do you think? Let's break it apart. Na plus, CHO2 minus. Are either of these pH neutral? Is pH neutral? Everyone agree with that? Why is Na plus pH neutral? Emma, why? Because it's in group 1 and it comes from NaOH, which is a strong base. The strong stuff is always pH neutral because it has no desire to not fully dissociate, okay? What about this CHO2 minus, Avi? Acidic, basic, or neutral? So what is it? It is the conjugate base of a, so that would be the acid that it is the conjugate of. Is that a strong or weak acid? Since only Bryce knows, Bryce, is that a strong or weak acid, HCO, CHO2? How do you know that? Because it's not one of the five strong acids. It's not that hard to like figure out this list, okay? Maybe take a pen and write it on your arm so when you have the test, you can use it. The test is a take home though, so write it on your notes. This comes from so this is a conjugate base. So it is a basic solution. So we would see that the sodium is neutral, the CHO2 minus is basic, it's got to be a basic solution, right? Pretty easy, right? When one of them is pH neutral. What happens when we have NH4 plus and F minus? Is this the conjugate acid of a weak base? Yes. So that's going to be slightly acidic. What is this? Does that come from a strong acid? Is HF a strong acid? So that comes from a weak acid. So that means it's going to be slightly basic. Uh-oh. We got something that's acidic and something that's basic. Does that mean it's neutral? What do you think? So we have to look at what is stronger. How can we tell whether, so I mean, think of it like this, right? Let's say you have a party, right? And you bring in a bunch of good people and and some bad people. Does that mean that the party is going to just be medium? What if it's like 10 awesome people and just two crappy people? Is it still going to be an awesome party? Most likely, right? What if it's 10 super bad people and three awesome people? How's that party probably going to be? Pretty crappy, right? I mean, every party should be good because you're partying. But at the end of the day, what if there's no bad people and some good people? It's going to be good, right? What if there's no good and a bunch of bad? It's going to be bad. So when there's the neutral, it's obviously what the other thing is. When you have one of each, acidic and a basic, we are going to have to quantify it. How do we quantify it? We have to figure out the Ka of one and the Kb of other, whichever one has a larger value. If the Ka is greater than Kb, Ka wins. The solution's acidic. If Kb is greater than Ka, the Kb wins. Solution is basic. If Ka is equal to Kb, the solution is neutral. That makes sense? So in this case, we have an acidic cation and a basic cation. We have to figure out the Ka and the Kb of each. So we can look up the Ka. Let me zoom in on this. The Ka of NH4 plus, there is probably, I mean, nowadays you could probably look up the Ka of NH4 plus, but really, if it was a test that was in class, I would give you the Kb of NH3, which is 1.76 times 10 to the negative 5. You would then have to calculate the Ka of that conjugate acid of that weak base, and you'd find that it's 5.68 times 10 to the negative 10. HF is a weak acid. It has a Ka that is associated with it. That means that F minus is the conjugate base, so it's going to have a Kb value, and you calculate that by taking Kw and dividing by the Ka value, and you get 2.9 times 10 to the negative 11. Of those two values, 1 times 10 to the negative 10, 1 times 10 to the negative 11. Which one is a larger value, Natalia? The Ka or the Kb? Which number is bigger, 5.68 times 10 to the negative 10 or 2.9 times 10 to the negative 11? The Ka is larger. Therefore, the solution would thereby be acidic. Everybody see that? So I've showed you how to do this. You'll have to do this on the homework and on the exam. Any questions? Break apart the ions. Figure out which one is which. If one or both is pH neutral, they're super easy. If they're both acidic and basic, then you have to find the Ka and the Kb. Any questions on this? All right. So that's chapter 15. When's that due? Friday? I should make it due sooner so you start it sooner. Okay. No one's going to remember how to do it by the end of the week. Do it tonight. I'm changing the due date to tonight, but not really. But just pretend that in your mind. So you force yourself to do it. All right. So chapter 16 is a lot of fun. Aqueous ionic equilibrium. Anybody know what antifreeze is? What is antifreeze? No one knows what antifreeze is? What does it do? Very good. Like, we can figure it out from the name, right? Why do you think we use antifreeze? It's used in automobiles. Why do we put antifreeze in automobiles? It's not for the windshield. That would just be windshield wiper fluid. You could probably put the antifreeze in there, but it's super expensive. Okay. If we were where I grew up, I'd be like, yeah, why do you need to know what antifreeze is? Because nothing freezes in Hawaii ever, right? But up here, if you live in Lake Tahoe and it's freezing, so you ever know what a radiator is? Radiator is something that puts water in. As your car engine gets hot, it runs water in and it cools it down. What happens if all that liquid in there is a piece of ice? What will happen to your engine? It will overheat and probably be super expensive. Most of us would just be like, hey, parents, my car's broken. Buy me a new one. And they'd be like, cool, thank you. But that's not everyone. So for those of us who don't have that luxury, you should make sure you have antifreeze. Really, in California, it probably doesn't make that much of a difference unless you're, but if you lived in Canada or Alaska or New York or Washington, you think it would matter? If you just, because in Hawaii, we just use water, okay? We had some janky cars in Hawaii, and we still have janky cars, and I would have to drive to town, and when it got hot, I'd have to pull over, I'd grab the jug of water out of the back, pour it in the radiator, wait about 10 minutes, and then I would drive again. And that was just standard protocol for cars in Hawaii. In California, they have, smog emissions, so your car has to be like pretty good or else they won't pass it. They don't have that in Hawaii, okay? So why is antifreeze bad? Each year, thousands of pet and wildlife die from consuming antifreeze. Okay. Most brands of antifreeze contain ethylene glycol. It has a sweet taste and it makes the animals feel drunk. If you were old enough to get drunk, do you think it's something that someone would want to do again? Most of us don't know, but someday you will. But people go back to the bottle, right? So what happens is that cat starts licking the antifreeze. It's like, oh, I feel pretty good. It keeps drinking it. In your liver, it gets metabolized to glycolic acid, and unfortunately, they die. So the take-home message is, sometimes, like I said, going back to Hawaii, if you had antifreeze and you have a leaky radiator, you just put a little thing underneath your car so it doesn't get in your garage, right? That fills up with this antifreeze. If you have a pet, what's going to happen? That pet's going to go and drink it. Be careful with that, okay? So why is glycolic acid toxic? It has to do with our bloodstream and our blood being something called buffered. So what we're going to learn about this week is buffers. Does anybody understand what buffers are? Not like if you're like the number one rated goalie in the nation, you're buffer than all other goalies, right? That what makes you a good goalie? Nope. But I had to throw it out there. So what is a buffer? Does anybody in here know about buffers? Should we learn about buffers? What is it? You have no idea? It is a solution that resists pH change. Okay. When I was in grad school, we were working on a sensor to implant into people to test their glucose levels. Could have been for diabetes, could have been for the ICU and stuff like that. I think I might have talked about that before, maybe with this class, maybe not. Regardless, one of the problems with our sensor was it had a big difference in sensitivity at different pHs. So we're like, oh crap, if we change our pH from 7.4, which is the bloodstream's pH, to 6.4, it gives different measurements than at 7.4. So we're like, oh crap, we're gonna have to figure this out. But then someone's like, don't worry, if your blood pH changes by more than half a unit, that patient's gonna pretty much die anyway. So if that's gonna be the case, it doesn't matter if we're getting a good read on the glucose, that patient's probably gonna pass away. So basically what that tells us is our bodies maintain a pretty strict pH level. Do we know what pH is? Yes or no? We've only been talking about it for 2 weeks, but I can't put anything past this class because we talk about something for 20 minutes and then I ask about it and we can't get the answer. So do we know what pH is, Valerie? So do you think it's important that our blood stays in a tight pH? What is an acidic thing that we eat? Oranges, limes, and things like that. If you eat limes, does it change the pH of your blood drastically and you die? I mean, if it did, we'd probably put the lemons on the do not eat list, right? So luckily for us, you eat a lemon, it does theoretically change the pH, but what happens is our blood is buffered and we will learn how to effectively combat the addition of an acidic component or the addition of a basic component. So what is a buffer? Anybody know? Sophia, you know what a buffer is? No, a buffer is something that buffs the ground. Yeah, it is. This is a buffer that you would use if you're cleaning the gymnasium or whatever else kind of things you buff cars and stuff like that. That's not the type of buffers we're looking at. It is solutions that resist pH change. And we got these little green creatures. You think our bloodstream has these little green creatures? I mean, who knows? We can't look that deep into the things. So what a buffer solution is, so how do you think something could resist pH changes? Emily, what do you think? How could a solution resist pH changes? What would be the easiest way? So if I'm adding acid, if I eat a lemon right now, put all this citric acid into my body, how does my blood not get super acidic? Pretty close, right? So what that means is, how do we combat the addition of acid? We add a base to it, right? What happens when an acid and a base reacts? What do we get? Huh? Water. Very good. Is water going to change the pH of our blood? No. So basically what happens is if we have a buffer solution, you see in red we have acid, in blue we have base. If we have a bunch of acid in here and a bunch of the conjugate base, this buffer works. So HF is a weak acid. Everybody agree with that? How do we know that, Bryce? Because it's not a strong acid. It's pretty important to know those strong acids, right? So we have our weak acid and we put in its conjugate base. So what is the conjugate base of hydrofluoric acid, Jack? F minus. Could we put F minus directly into a solution? Can we just put ions into a solution? The answer is no. You can't put in ions. So what could we do? Honey, how can we put F minus into solution where we only want the F minus to be reactive? What could you pair it with? If it was H plus, that is going to be an acid, and now it's no longer going to be a base. So if we just want F minus, what's the best way to do that? Donatella? Good thought, but no, water is neutral. We need a cation, Bryce. Why would we use sodium? That's correct. Because when you add sodium anything, the sodium just stays dissolved. Is it going to affect the pH of the solution at all? No, it's not. So this is basically what we call a spectator ion. Remember spectator ions from Gen Chem A? When you had to do net ionic equations and things like that? Of course you don't. That was a whole semester ago. We can't even remember the beginning of class, right? So we're going to add the conjugate base with some pH neutral cation. We could get fancy and use potassium or calcium, But really, we just use sodium because sodium is the cheapest cation that there is, okay? That's why, like I said, with all of those anions where we had nitrate for the different cations, if you want to vary your cation or your anion, you would always use sodium, and then you can substitute in whatever it is. So if we have F minus in solution and we have HF, okay, so this solution contains the weak acid HF and its conjugate base F minus. Does everybody at least understand those terms? Okay. Now, what happens to this solution that has HF and F minus, Robert, if I add some HCl into it? Is one of those ions pH neutral? The chloride, yes. So just like I said, sodium we don't really worry about. When we have something that's a conjugate, we're basically just adding H plus and Cl minus. Cl minus is pH neutral. So the Cl minus doesn't affect the pH, right? But is adding H plus going to affect the pH of this solution? Yes, it will. So if we just add this HCl to a system of water, what would you expect to happen to the pH? Any thoughts on this? What do you think, Michelle? If we add HCl to water, what's going to happen to the pH? Up or down, or stay the same? Try again. Very good. Why would the pH go down when we add strong acid, Ricardo? Nana? Why would the pH go down when we add strong acid to water? Because you're adding acid and pH going down is acid. Everybody get that? And it's going to go down a crap load, okay? Now, what happens if we add HCl to a solution that contains HF and F minus? What could happen in this case, Jackson? So once again, we have a solution that contains HF and a solution that contains F minus, and we're adding H plus in the form of HCl. The Cl is meaningless. The Cl minus is meaningless. The H plus is the thing that would affect the pH, right? So if we add it to water, the pH goes down. What happens if we add H plus to this? Do you see anything that could react with that H plus, Jackson? The H plus is going to react with the F minus. Everybody see that? That's going to form HF. HF is a weak acid. By generating a weak acid, the pH will go down. But do you think adding a weak acid would make the pH go down a lot less than adding a strong acid? Kayla, does that make sense? So in this case, when this solution has a buffer in it, adding H plus causes the pH to drop a very small amount. Conversely, what happens when we add NaOH? NaOH is Na plus, which means crap, but now we're adding OH minus. If we add OH minus to straight water, what happens to the water, Merve? It gets very basic, right? Because you're adding straight OH minus. But if we add this NaOH, what could happen in this case? Avery, what could happen? If you add NaOH to this buffer solution, the buffer solution has acid and its conjugate base. This is a slightly basic ion. This is a weak acid. So I would say probably this solution would be slightly acidic. We can adjust the ratio to make it at the pH we want. The pH would go up. Do you think it will go up the same amount as a non-buffered solution? The non-buffered solution is adding OH minus. You would be boosting the OH minus directly. When we add this OH minus, what do you think could happen, Kayla? In this buffered solution right here. Yes, but it's going to increase it way less. How? How does the buffered solution make it not go as bad? It reacts with the H in the HF. Everybody see this right here? What does the H plus the OH minus make? Water. And it's going to add some F minus. F minus is a slightly basic solution. So instead of adding straight hydroxide, which is straight super basicness, you're going to be adding you're going to neutralize that straight basicness, but you will be making a little bit of a conjugate base, which is slightly basic. Do you think the pH is going to go up as much if you add straight base versus weak base salt? The answer is it will not go up that much. Okay. So that's how a buffer works. You can do the same thing with a weak base and its conjugate acid, but you cannot use a strong acid and its conjugate base. Give me a strong acid, Zeus. Yeah. You don't need your notes. Give me a strong acid. Uh, huh? HI is a strong acid. Everybody agree with that? Okay. So if we have HI, what would be its conjugate base? I minus. Can we add I minus directly? Let's add NaI, which would basically be Na plus and I minus. Now, when we add something like HCl, which is basically just adding H plus, could the conjugate base I minus react with the H plus to do what the weak acid's conjugate base did? What do you think, Bryce? Would the I minus grab the H plus? That's correct. Why not? Because what is the definition of HI? If I have 100 of these, I make 100 H pluses and 100 I minuses. That means that this I minus has no desire to ever grab a proton. That is the definition of a strong acid. Its conjugate base has zero desire to ever be bound to a proton. So if you try to use a strong acid and its conjugate base, that is not a buffered system. The I minus is like, I'm just here to show up. I'm not listening or paying attention. Does that sound like anybody? And if you have a guilty conscience, then that's you. But if not, then keep learning. Okay. So what happens is when you use a strong acid and its conjugate base, that I minus is just sitting there doing nothing. You add acid, it's just going to increase the pH. When you use a weak bases by definition stay stuck together. So if you put a bunch of that weak conjugate base in there and then you introduce some H plus, it's like, hey, I like being bound to the H, right? So it goes and it grabs that H and it keeps it from making the acid be bigger. So to pictorially represent, or to numerically talk about this, buffer solutions resist change in pH when an acid or base is added. I showed you how. They act by neutralizing the acid or base that is added to the buffered solution. When they neutralize it, they do make some of the conjugate acid or base, whichever one is reacting. But it makes either a significant amount of weak acid and its conjugate base or a significant amount of the weak base and its conjugate acid. These will not affect the pH as much as putting in the straight acid or base that we're putting in. So our blood is a buffered solution that contains H2CO3 and HCO3 minus. So H2CO3, is that a weak acid? Cade, is that a weak acid? How do you know? Very good. HCO3 minus. So that would probably be put in as Na plus HCO3 minus, sodium bicarbonate. That's basically baking soda. Okay. So our blood has carbonic acid, which can be made just from dissolve. If you blow into a cup of water, you are changing the pH because the CO2 dissolves in that water because carbonic acid is dissolved. Baking soda. Our blood, if we eat citric acid, H citrate, I don't know what the formula for citric acid is. When you eat a lemon, your blood's like, oh crap, we're adding acid. What's it going to do? make the pH go down drastically and kill us? Anybody in here died from eating a lemon? I don't think so, right? Because you're all here. So luckily for us, our blood is buffered. So the H plus comes in though, and our blood's like, oh crap, oh, send some of the base over here, and it will generate some H2CO3. That's adding some weak acid. It's still gonna drop the pH a tiny bit, but not as much as just eating the acid. What if we eat something basic? What's a basic food? Anyone know? Huh? I think bread's just like absorbing stuff, so it like helps with acid. But I feel like yogurt might be basic. I don't know. I think most basic foods are pretty poisonous, to be honest. But if you were to add some base to your body, the OH minus could be like, oh, I'm gonna give you one of my H pluses, make water, and now I'm gonna just make more of my conjugate base that we see here. So that's how buffers work. Pictorially, we mix weak acid and its conjugate base. Notice how we're using a weak acid HC2H3O2. Why is sodium acetate the conjugate base in this case? Because we couldn't add just C2H3O2 minus. Okay? So here's how it works. When we have a water system, so if we have pure water, pH starts off at 7. We add acid. What does that pH change to? Can we see that? 4.0. Is that a big change in pH? That is 1,000 times more H plus than pH 7. Okay? If we add sodium hydroxide, the pH drops to or increases to 10.5. Is that a large increase in pH? Yes. If our blood was just water, would that be drastic to us? 100%. When we use a buffered system, we can make that pH whatever buffer, whatever we can make that buffer whatever pH we want. Let's just say we have a pH 7 buffer. When we add the same amount of acid as we added over here, the pH goes to 6.9. So 7 to 6.9. Is that a drastic change in pH? It is slightly more acidic, which makes sense because we're adding acid, but it's far less acidic than just water. And the same thing when we add the base, NaOH, it increases the pH to 7.1. Now we see how a buffer works in real life, right? So if a strong base is added, it is neutralized by the weak acid. If NaOH is added, it is neutralized by the conjugate base. It is neutralized by the, so if a strong base is added, it is neutralized by the weak acid. If the amount of, as long as the amount of NaOH is less than the amount of acetic acid present, the pH change will be small, okay? All that's saying is, if we had 1 molar HF and 1 molar NaF, we could buffer this system as long as it is less than 1 molar HCl added, right? Once we add more than 1 molar, all of this, so if we're adding acid, it's reacting with the F minus. Once all of this F minus is gone, now it's going to be an unbuffered system and the pH will start to drop dramatically. Same thing here. If we have 1 molar HF and 1 molar F minus, which is the NaF, we can neutralize as much sodium hydroxide that is added as long as it's less than 1 molar. If you add in 2 molar, the first molar of that sodium hydroxide will get neutralized, but then there's no more of that conjugate. So a better buffer system is obviously going to have more of each thing than less of each thing, right? So one way I like to think about it is if, so we use the hat analogy, right? Let's say everybody in here could have hats, right? And the hats are the acids. Well, what if half of us had hats and half of us didn't have hats, right? And now we bring in a bunch of hats. Do we have some people without hats who could take on those hats so that there's not just hats lying around? Those hats would be like super acidic solution. If half of us don't have hats, couldn't we be able to take hats that are coming in and put them on the people without hats, right? That's how a buffer works. Conversely, if there's people coming in wearing hats and we had an accumulation, I mean, this may not the greatest analogy, or now if there is, what would be the other thing? So when hats come in, the people without hats can put them on. If people come in without hats and they want hats, right? The people who have hats can give their hats to those people without a big drastic change in the pH also, okay? And that analogy is not great for the hydroxide part because why is someone coming in without a hat? They're just coming in to demand our hats. How many in here of us would be bummed? 2 of us. Very nice of us all not to wear hats today. The sunniest day of the week, and we're all gonna get sunburned. You all know about sun danger. I don't have to lecture you on that, right? And lecture you on enough. So basically, we know how buffers work. So we can think of it. If we have HA and A minus, and we add H plus, the A minus reacts with the H plus, the HA goes up, the A minus goes down. Everybody see that? So we could react. So if we had 4 HAs and 4 A minuses, this demo is showing that we're bringing in 1 H plus. That 1 H plus, this 1 H plus that comes in is going to go and put its H plus on one of the F minuses. So now we still have the original 4 HFs, but one of the F minuses became another HF. Everybody see that? And we had 4 F minuses to start. Now we only have 3. Is the solution still buffered? Could it still react with H plus or OH minus that comes in? The answer is yes. Going back to the original, 4 and 4. If we had OH minus, the HA is like, oh, I'll give you my H to make water. That's not going to affect the pH. But I now, instead of having 4 HAs, I only have 3 HAs left. And instead of having the 4 original A minuses, I now have a 5th A minus that was formed. Everybody see that? So it's kind of like you have, and then what is a buffer, right? If you are in a class and you have an A, what does that mean? What's your percentage usually? 90%, right? So if you want to go into the final with a buffer, what kind of percentage would you like to have? Let's be real. Okay, just kidding. So if you have a 95%, you have a buffer of 5% that you can like blow. And like, let's say you get an 80 on the test. As long as you have enough buffer points to neutralize that less than an A, you can maintain an A, right? So if you have a 91%, you still have a little buffer. If you're at 89.99%, you have no buffer. You have to get an A or better on the final, right? If you have 100%, I mean, and once in a while I would be in a class and like they would have extra credit and I'd be like, I would calculate what grade I needed. Like one time in math, I was like, I need a 64% on this test because I like got A's on all other ones. So I didn't study as hard because, you know, finals week, you have like 4 finals. I mean, nowadays, it seems like no one has finals anymore. But you can focus on the classes that you need to do better on, right? Because you have a bigger buffer in that. Same thing with this. The larger your buffer, the more you can neutralize. So to summarize all this that we've talked about, buffers resist pH change. Do we all know how that works? Yes? I can call on anyone in here and they'll tell me the definition. Yes? No? Amanda? I'm just kidding. I don't want to put you on that. So the buffers, you could have just read the board though. A buffer contains significant amounts of both a weak acid and its conjugate base. So let's be sure that you know it cannot have strong acid and its conjugate base. That is not a buffer system. Okay, it has to be a weak acid and its conjugate base, or it can be a weak base and its conjugate acid. We'll look at that. The weak acid neutralizes any base. The conjugate base neutralizes any acid. Okay? Yes, Jack. The buffer does not need to be neutral by any means. So we're going to learn that we're going to like actually learn how to make buffers of different pHs. And based on the ratio of your acid and its conjugate base is going to vary the pH, right? So we're going to decide which acid is the best one to use. So the reason why our blood uses the carbonic acid and sodium bicarbonate is because that gives us a buffer roughly at the physiological pH. If you use the stronger weak acid, it would probably have a pH starting lower if you were using equal. If you're using a really weak strong acid, it would probably have a basic pH when you're doing that kind of stuff. So these are all things to consider, and that's where we'll end it. Like I said, when we have 0.1 molar acetic acid just in water, the pH is 2.9. 0.1 molar base, it's 8.9. When we mix the two, it goes somewhere in between. We will calculate how to do that on Wednesday. I don't know what we're doing in lab this week, but have fun with it. Aloha.